There we go. Hi, everyone. Welcome to Toronto Data Workshop. Today, we are very lucky to have Sean Taylor from Motif, who's going to talk about causal analytics with event sequence data. Sean's done a variety of things over a course of a really interesting career. He's been a data scientist, a social scientist, a statistician, and a software developer. But in particular, today he's going to talk to us about this some a new venture of his, relatively new venture of his, around event sequence data, and he started a whole business around this. So a very exciting time. Thank you very much for joining us, Sean.
Yeah, thanks for the invitation, Rohan, and it's a real pleasure to be here. And I was just thinking about my relationship with Toronto, and it's like the largest city in North America that I've never been to. So this is the closest I'm getting to meeting people from your city. But it's a real pleasure to be here virtually. I hope to visit the city someday. One of my coworkers is from Toronto. He says lots of great things about it. So and it's a good opportunity to spread some of uh, the work that I've been doing and talk about it and get feedback. So I want to ground this in just before I get started on the talk, just like why am I doing this kind of work and where is it coming from? Well, Motif is a product that we've been selling, and the thesis behind the product is that like exploratory data analysis, specifically from product analytics, which is a space that I've been adjacent to for a long time, has been kind of constrained for a while. Like there's lots of things that people would like to do and problems and questions that they'd like to work on, but that the tools that they have available aren't powerful or expressive enough to do that. So we've been working on trying to improve that situation. The methodology for that is, I think, kind of like almost like qualitative research. So I've been over the course of the last two plus years working on this company, talking to a lot of practitioners about what they're doing in practice and trying to help understand what they're doing, what their goals are, and like how we can build things that help improve that. Um, and so the kind of first observation that we made, and this came even before the research, is that there's this type of data we call it event sequence data, but it has many different names. It hasn't standardized as fully as other types of data, but it's very, very common in companies that have digital products because they can instrument the product in various ways. And usually this is like a lot, like you can think of this as like logging, people call it instrumentation, people call it eventing sometimes, but it's basically just like putting areas in the code base where when something happens, you fire an event. And it creates a really rich stream of data, and it has a sequential property to it, right? It always has a timestamp associated with it. And then there's usually a user ID or some kind of identifier. And starting from the premise of like, this is the raw stuff of observation. This is our perceptual system for the settings that we work in. There's things to leverage about this particular form of data. And if you're an economist, I think it looks a lot like panel data. It's sort of like a generalization of panel data where you have kind of more fine-grained measurements and a high-dimensional outcome space rather than like having kind of like, maybe just one or two scalar variables. You have like this whole vocabulary of different events that can be triggered, and they can be triggered by the user doing things or by the backend system, like the actual computational engine doing things on behalf of the user. So there's this stream of events, and they describe what's happening in the system, and it's kind of like a cross section of longitudinal measurements. And so we start with this as a primitive. And the question is like, what can we leverage about the structure to help people do the kinds of tasks that they're working on? And then to kind of marry that with like, okay, well, we know what kind of data we'll have available generally. Well, what kinds of questions do people tend to work on in practice? And I came up with this taxonomy a little bit pretty early on in our company, and I haven't quite seen it laid out this way elsewhere. I don't think these are like novel ideas, but I think that they helped me ground what we're trying to accomplish. And so I want you to take away anything from this particular talk. It's to start, maybe thinking about some of the work that we do, both in like science and in business in this way, because I do think it's a helpful grounding. So in this 2x2 quadrant, designed for presentation to MBAs who have a framework, we have on the x-axis is a cause of some kind, and on the y-axis is an outcome of some kind. It's not a cause effect. It's like the outcome is just a measurement, right? So an effect is an outcome minus another outcome, but an outcome is just like what happens after a cause. And when we have this XY relationship, this is very standard statistics, right? And most of the work that is done is in a regime where you have predefined a cause and effect, and you're testing or measuring relationship between two variables that have already been sort of like created and defined. And so that's this lower left-hand quadrant. I would call this almost like the normal scientific paradigm for businesses, is that we hypothesize a cause-effect relationship, and then we go and try to explore it. These other quadrants are actually valid scientific activity, right? Like they're questions that come up as we work on things, but that they are a little bit less well developed in terms of methodology. So the other three quadrants are when you don't know what the cause is, but you observe an outcome. So this something happened, and why did it happen is a very common question. Then there's the we did something, or we observed a potential cause and we don't know what the result of it was. So this happens a lot, like if you change something about your product, or your competitor does something, or something in the environment changes, you might want to try to understand like what the results of those things were. And then there's just sort of like general theory building about the setting that you're working in, which is like, can I just find cause effect relationships so I can start to build a mental model of like what's happening in this system. All three of these things are done relatively informally and like without kind of standard methodologies. So that's kind of the thesis that I'm starting from. So like if we had to outline the system right now, as we get closer to the origin of this coordinate system, we have more and more standard methodologies that we can use. They're reliable and they're well understood. We have fewer rigorous methods for answering the other kinds of questions that come up in practice. In the lower left-hand quadrant, it's pretty standard kind of work in general. Like in my experience at tech companies, that we either run tests, so there's an A/B test, or we launch a change on a specific date, or we observe a competitor make a change, or there can be other things that can happen. And when we have control over that cause, it's usually pretty straightforward to measure the effect of it. Like we have technology to do that, depending on what kind of cause that we've implemented. We can measure some outcomes and then determine what the relationship was between the cause and the effects. This is obviously accelerated by some new software that's been developed and like approaches that have been developed in the last few years. But like A/B testing frameworks and tools are very well proliferated at this point. There's things like synthetic control methods, which are very popular. Things like causal impacts, where we can do event studies just on time series data. And the thing about these methods is that they're so well established and reliable that we can start to use them like as the inner part of a loop and do like kind of optimization on top of it. So when we can do causal inference in an automated way and get it in an unbiased estimate, we can start to explore a design space and try to find what the best possible of our system is to create the outcomes that we want. So like one like kind of concept that I use when I think about this a little bit is like this, I call it the experimenter's three tensor. I totally made this up. No one else has ever talked about this, but it's a kind of common conditional probability or conditional expectation that we reason about, which is like that there's some outcome that we care about. We want to make an estimate of that. We want to condition on some things. Some things we can change about the system. Some things we can't change about the system. And so we really, in general, want to be able to estimate this conditional expectation function as accurately as possible in a regime where we have maybe multiple contexts, multiple treatments, and multiple outcomes. And as you kind of scale this tensor out to more and more dimensions, you get a richer and richer view of like your interventional capability within a system. And so when I worked at Lyft, this is super common to think about things this way, to have like a lot of dials and knobs that we were able to change, and we could start to like run experiments in a rigorous way to kind of fill in estimates in this tensor of like, if we did this in this setting, then this outcome would be estimated to be about this kind of value. That function estimated, and you have an unbiased estimate, it becomes like the target of optimization. So companies will tend to then say, hey, like we know this function pretty well, we have good estimates. So then we can go run, like we can try to run some maximization of with respect to A of this function and establish some goal. and either hill climb or directly optimize their way to a better business outcome. So I call this like this is like normal science for a business, which is like find interventions that make things improve or make things worse, and do more of the things that make things improve and do less of the things that make things worse, and like your business gets better. And so this is kind of like the way that most people. It's a well-established methodology, and obviously there's lots of specifics to fill in about how to do this, but like that the actual concepts are well established, and the methodology, there's a wide range of methodologies that we can use. But the other quadrants are like kind of fuzzier, right? Like at least when I started this project, I didn't feel like I had a good handle on like what are the methods that people use to do these things and what are the best ways to do it. But just because you don't know have good ways to do it doesn't mean it's not a valuable activity. So like in unintended consequences quadrant, that upper left-hand quadrant, this happens a lot in business, is that people run an experiment and some non-hypothesized things occur as a consequence of the experiment, and that people spend a lot of time trying to reason about, well, why did that happen, or what were the actual implications of this thing that we did. So there could be a benefit that you weren't expecting that might generate some new ideas, like, hey, we made this change and actually something good happened that we didn't think about in advance, and like that might suggest another thing that we could do that would generate a similar effect. Or you can observe mistakes, like maybe you cause some harm by instituting a change and it wasn't hypothesized in advance. And so discovering these outcomes is a relatively useful business activity. And it's an inherently exploratory analysis. It's a hypothesis generation task, not testing a hypothesis that maybe you had originally stated. In the lower right-hand quadrant, what I call attribution of outcomes, most things that occur that are like good or bad in systems, I have a kind of what I would call polycausal property, where they're caused by multiple things. So like that there's usually this simplistic, like this causes this, is not really a reasonable hypothesis. It's usually some confluence of factors. And then you might want to understand the confluence of factors better. And there might be some things that you don't actually know about in advance that you'd like to like know more about. Like, oh, maybe and people have lots of ad hoc ways of generating hypotheses about causes for outcomes that they're interested in. But that this is not a super rigorous activity in general. This is something we kind of like delegate to human intuition and personal experience a lot of the time. And people sometimes call this like root cause analysis, or like, investigatory work, where we're trying to find the reason why something good is happening a lot. We want to know why, or something bad is happening, or users are complaining. And, this is like a super common data practitioner task, but it's just like, hey, all these models that we built for causal inference just like don't directly apply here, unfortunately. So I want to focus on this quadrant today because this is what I've been working the most on, and I want to explain why I think it's such an important piece of the causal inference landscape. And it's not a new idea to like to motivate it, because I think lots of people have been observing for a while that like if you study causal inference, that there's a specific form of question that we tend to answer, which Gelman and Imbens in a 2011 paper called forward causal questions, which is like these hypotheticals about if we implemented some intervention. And this makes sense that like economists and social scientists have focused on this, because it's kind of like policy evaluation work. Like, oh, I would like to know, like, if we did something different in the world, like what would happen, and would it be better or not? It's a super common and important set of questions. But they highlight this other kind of causal question, which is like reverse causal inference, or the search for causes of effects. Like what causes why? Why do more attractive people earn more money? Why does per capita income vary some by country? We are looking for explanations for phenomena that we observe in the world. And this is a much harder set of questions, and because of that, we've been sort of focused on like looking where the light is instead of like looking where the value might be here, and we just don't have methods to do it. In that same paper that I was citing there, there's this nice quote from Kaiser Fung, who's a working practicing statistician, and he works in the corporate world, and he writes, a lot of real world problems are of the reverse causality type. Like over 10 years ago that he's writing this. And I don't honestly think that a lot of intellectual progress has been made on this problem in the intervening time. And it's I think it's because it is kind of hard, and it is kind of like a hybrid of an estimation problem and a search and intuition and modeling problem, and so a lot of the machinery we've been developing just like isn't exactly suited to these type of questions, and I think that's so. The first 10 minutes of me talking so far has just been like, why am I working on this? And I hope I would convince you that it's important. The process by which we imagine this kind of causal discovery work fitting into a business is that you use it to imagine interventions that you could employ that don't exist yet. And so experimentation platforms are a very common tool at businesses where they run tests and they analyze the experiment results. But there's this informal process of like, where do hypotheses come from where we got the tests come from somewhere. And they come from ideas that people have, and those ideas are essentially hypotheses about cause-effect relationships that they can control. And our theory in general is that this is we call this exploratory causal analysis, whereas we don't have experiments, we cannot get like unbiased estimates, we cannot get policy evaluating policy estimates suitable for policy evaluation, but we can get estimates suitable for generating hypotheses at this phase, and that this is a valuable activity because it allows us to run better experiments, hypothesize better interventions, and then that makes the business better because we just have more of an imagination for like what we need to improve in order to make things better for users. Which is just to highlight like the role of this as like a scientific activity. This is theory building. It's kind of like that when you are fleshing out a cause effect graph, you're adding new nodes to the graph, and you're adding or removing edges to this graph. You can build this graph out through this activity of finding like antecedents to nodes that you already that you have in the graph, or like descendants to nodes that you already have. And then by doing that, you can kind of like build up a graph. And this is how science works in general. We just don't formalize the like, in a lot of causal inference, it's sort of like you write down the DAG from your own intuition rather than like letting the data give you a DAG. And so causal discovery, I think in a lot of ways is just sort of like where does the DAG come from? And like, maybe there's a way to do it from data, or at least to start as a starting point for settings where we don't have a lot of domain knowledge. It makes sense to build DAGs from intuition in settings where we have direct observability over the system, because like we are seeing it play out. The data collecting is going into our perceptual system. But if the data is being generated by people all over the world using a digital product where we don't directly observe them at all, then maybe it makes sense to like rely on like this telemetry instrumentation that we create as a way to like help us inform what theories we might have about it. And we'll have to rely on this distributed digital perceptual system to do causal inference in the future. How are we going to do that?
Sure.
Yes.
1 minute. If you could just spend like just 1 minute just briefly explaining DAGs in a little bit more detail, just in case folks are unfamiliar with the term, please.
Yeah. Sorry, I'm assuming some background on the part of the audience for causal inference, but in causal inference, one of the key tools is called a directed acyclic graph. In those graphs, we have nodes, and the nodes represent like variables that we observe, and the edges represent causal relationships. So if there's an edge between two nodes, it means that like changing this variable will cause this variable to change. If there's no edge between them, it means changing this variable will I'm trying to think of a non. This variable will not cause a change in this variable would be like one interpretation of this. And this is like it's a model, but it's not a statistical model. It's a conceptual model of a process, and it can be turned into a statistical model. And this is the foundation of a lot of causal inference work.
Thank you.
Yep. Yeah. I'm assuming some background here from folks, and so like if there's stuff that I'm happy to elaborate on anything here just to make sure that it's more clear. Okay, so I'm going to go through like how do people do this now and why I think it's kind of deficient, and then I'll talk about like what we've been doing to try to repair that deficiency. So a lot of data, if you think about the data I was talking about as having two coordinates, right? It has a user or an identifier. It's like who was using the product and at what time, and then the dots are observations. We've like observed this event happen to this user at this time. And so we end up with this kind of like two-dimensional coordinate system is very, very common in business data because it's because it comes from this event data that we just talked about. You can aggregate this data in various ways that are heuristics for making it lower dimensional than it really is. So it exists in this kind of like high dimensional space. We have users, time, and then event type, and then other properties of the event. So it's a high dimensional data set, but what we can do is we can just compress it by, say, aggregating by time. So turning it into time series data is very common, right? You just like count how many occurrences of an event that you have by each time bucket, and then you get like a kind of time series or a line plot. Or you can do user level aggregations where you count up for every user how often they did something, or rates and stuff like that so you do aggregation at the user level, or you can cross the two. You can do user cross with time, and then now you have this panel data structure, super common in econometrics. And if you're doing this aggregation is a modeling step. You have made assumptions about the data at this point that then allows you to use other kinds of models downstream. So like if you have aggregated into the time dimension, you can use time series analysis to analyze the data. You can use forecasting techniques. You can do anomaly detection. You can do things like causal impact on top of the data. If you do you can analyze an A/B test. You can study user level policies. And if you do user time aggregation, you can use methods from panel data and things like synthetic control to study the data. And so like this aggregation step is a pre-modeling step, but it does make assumptions and it does discard information. It's important to note that anytime you aggregate data, you like are discarding low-level information that's available. And so like because of that, it's a lossy transformation. And these methods that we are very standard and useful, but they don't have access to the full data generating process because we have already pre-aggregated data. It's a super common problem in statistics in general, right? It's a bias variance trade-off. So if you aggregate things, then you create like a higher bias, lower variance measurement that then can be used in other methods because it's lower variance, it looks more precise. But it's also like it's higher bias, right? It is removing information that like could be valuable for the particular question that you're studying. If you needed to model event sequence data in the richest way possible, which is the lowest bias version of this is to think of it as a generative process where the event stream is generated one step at a time. So the data look like this. We have a sequence of events, each observed in a particular order. And you can think about various kinds of probability distributions on top of that process. And a simple one is like kind of conditioning on some prefix and making a probability estimate over what happens afterward. This kind of like a forecasting step. This also happens to be the problem that large language models solve. It's like, you input this amount of text and then it can generate completions to that text. So it is in fact the same idea. It's just now instead of text tokens that they happen to be events, but it's a very similar kind of model. And so there's many possible conditional probability distributions on top of sequence data, right? You can make a cut at any point and make a probability estimate of like what happens at any other point. And then what I want to talk about is in this causal sense is like what I call an interventional distribution on event sequences. So this is a little subtle, but think about like we've observed these first of 4 events for a particular user, and then this 5th event, like it could happen or not. And you can think about a world where you're often in causal inference, it's convenient to think about like being omnipotent. Like I can make something happen. I could like assign a certain state to a user. What if I could make an event happen at event 5, like whatever event that I want? Then what would happen afterward? And how would it be different from what happened with the actual event that happened at event 5? And so like there's lots of, maybe the simplest way to think about this is like, let's say a user is going through a checkout flow for a product, like they're trying to buy an item in an e-commerce store. And one of these steps is like getting a user to click on the next step on a process. Well, like we can't make users do that. They just do it on their own or they don't. But we could make the button bigger, or we could make it more clear that that's what they need to do next, or that there's interventions that can cause events to occur with higher probability. So we do have interventional control. It's just sort of like not readily available to us. We have to build or we have to redesign products in order to make events more or less likely. But they're still reasonable counterfactuals to think about. They're reasonable, like it's okay to reason about like what if we could make events happen at higher probability in certain settings. That's the thing that kind of like comes up a lot. So this distribution is what we'll be targeting in this study is like if we could make this event happen, what would happen in the future given this setting. So we really take the sequence and we can kind of partition it into three different pieces that like, and it's kind of like a beginning, middle, and an end of a story, or if you've ever done like performance reviews, you've heard of the situation, behavior, outcome, or whatever. So it's like in this situation, this occurs, and then this is the result. And it's kind of convenient to apply the same idea to sequences, to carve them up into pieces and give them a role in the analysis. And so now we end up with like these are standard variables for like a cross-sectional model now, where we have like an outcome variable which we compute from what happens afterward. So outcomes can be things like, did the user purchase a product in the next 30 days? Or what was the revenue from the user in the next 30 days? Or did they come back and use the product again within a week? Or something like that. Can be defined in a very flexible way. Anything that you can compute from a function that's run on top of these variables can be specified as an outcome. And there's a context, which is like everything that's happened up until that point, and it can be very long, right? So users use products for months or years, and so there's many, many, many events, and they describe the state that the user's in at that point in time. And what we do, and what the perspective that we've taken is that we need a learned representation of the context that the user's in. So this is, you can think about this as like an embedding is the way that we call it in deep learning, is that we're trying to take a lot of data that is potentially unbounded and compress it into some representation that has a kind of more convenient way to work with it, but that retains most of the relevant information for the problem that we're trying to solve. And then in the next event, there's like whether they did a particular thing or not. So like this event denotes like, did they click the button that advances them through the process, or did they not? And if they didn't, it doesn't mean they're not going to buy. They could just buy later, but it does maybe, it'll be associated with some drop off or some lower probability. So we're interested in, this is our hypothesis, is that this treatment will cause some change in the outcome. And the context is something that we want to use as like a way to think about whether that situation matters for that treatment in various ways. And typically it's going to be related to some kind of confounding that we have. So back to that, the thing, Ron's question was very, very prescient, because we have to talk about DAGs to get to this next step, is that in a causal DAG, this fundamental problem that we're trying to solve is that we want to measure the effect of T on Y, which is this arrow here. But there's kind of always in the looming in these settings is like an unobserved thing about the user. There's a variable that we cannot measure, but that causes them to behave in a certain way previously, causes them to be the kind of person that would take that action or not, and also causes them to go and do the thing in the outcome in the long run. This is typically something like how interested the user is in, if it's an e-commerce site, how interested are they in buying? And people who are interested in buying will tend to buy, regardless of what happens in the rest of the model. They also tend to take steps and processes that advance them toward buying things. And they also tend to do things that indicate that they're likely to buy, like they are more active and use more features and things like that. So the U variable is very kind of important, but we don't observe it is the problem. And so it makes it hard to, it creates alternative explanations for why we would expect to see a correlation between T and Y that we wouldn't, that is not a causal correlation. Could just be, have nothing to do with like T causes Y, but they're still very correlated variables. So maybe this is like, I don't want to get into this too much, but basically what's going to happen is that we're going to look for, by trying to adjust for and control for X, we get a cleaner estimate of the effect of T on Y. And that's the key idea behind our procedure. So we're saying like, we took everything the user ever did, and it's a signal about something unobserved about them that we don't know. It's a variable that we'd like to know, but we don't. the best proxy for that is going to be everything that we know about them up until this point in time. So if we could find a perfect experiment, it would be find somebody who had the exact same historical behavior as another person, but where T happened for one, but not for the other, and we can pair them up like twins. We don't actually have any twins. What we have to do is like, because the histories are very long and it's impossible to find an exact match, but we got to find people that are similar enough to make a fair comparison, and that's what we try to do. Let me skip over this part. So how do we use this in practice? Is like, and I want to talk about like why this is a useful tool. Is that if we get an estimate, let's say that the X is the context that the user's in, and then the event T either happens or not, and then there's some outcome that is observed later. So this is the 3-variable setting that I described. If we could match all the users on the context just perfectly, then we could say, how common is this situation? That's the probability of being in situation X. Then what do we have over that next event and whether it happens or not? This is something that we have to use domain knowledge to ascertain. Then we can look at the conditional probabilities of probability of the good outcome happening if the event happens, or the good outcome happening if it doesn't happen. And the difference between the two will be like some measure of an effect. Like if we could make this event happen, the good thing would happen with a higher rate, and if not, it would happen at a lower rate. And then we want to also make sure that the difference between these two settings is causal. Like if we did make an intervention that leveraged this knowledge, that we would still see that effect in practice. So we can fill out this table with numbers and get some examples of like, here's a user where they have a 25% chance of clicking the button, and if they do, they have a 75% chance of going on to buy the product. Whereas like if they don't click the button, they only have a 20% chance of going on to buy the product. Purchases from getting the user to click this button or whatever. But the question will be like, is that estimate valid enough? And could we actually intervene on this thing? And if we can intervene on it and that this estimate will persist if we do intervene, then we have an opportunity. And this is an opportunity to improve the product or to like, make the business process better. So I'm going to ground this in an example so that you can kind of see how this works in practice. This is an example case study from this product called Amplitude, which is like a kind of a competitor for Motif. They're much more established, a public company with like, billions of revenue. They have this example from this Calm app. So what they discovered when using their tool was that very few users, fewer than 1%, were finding and using a reminder feature in the Calm app. So there's a feature in the app that will remind you to meditate. And not that many users were actually using the reminder feature. But they also found this correlation is that when users did use the reminder feature, they had a 3x increase in their probability of using the product in the future, what we call retention. So setting daily reminders seems like a very plausible thing if we could get users to do more of it, that they will use the app a lot more in the future and retain and stick around and get the benefits of meditating. So what they did was they ran an experiment where they nudged people to use daily reminders by making the feature more prominent in the app. And so effectively what that's doing is like making the event of setting daily reminders more probable. And then they're hoping that at the end of that we didn't just have a confounding problem where like all the users who set daily reminders are also the kind of users that were going to stick around anyway, because those are just more motivated meditators. And because they ran the experiment, actually, they did get a causal effect, and they're able to estimate that it did increase retention by the same amount that they found in their observational study, where they weren't able to intervene. This is kind of convenient to them, but it ends up it's the perfect story, and it goes back to our prioritizing hypotheses that come from the data. It's like the data didn't tell us that this cause was going to work, but it suggested that the cause could work, and then when we tested it, we were able to validate it. So just to put that, this is like a little intro to causal inference tag for people that aren't familiar. The way we would model this would say future app usage, we hypothesize is positively correlated with scheduling daily reminders. But there's a confounder, which is just like interest in meditation will tend to cause people to schedule daily reminders and also use the app more in the future. And then in the experiment, what we're able to do is like implement a product feature which definitionally increases the probability of scheduling daily reminders. So we know that because it's like designed to do that. And And then when they ran that experiment, they found that that this path here actually, that there was no cause of interest in meditation on scheduling daily reminders. It was basically random whether people were finding this feature or not. Okay, I only have a few more minutes, so I just want to get through how we automate this process. So the question becomes like, think about this call map example. They only found one thing, and it was like they were searching through the data in a manual way without a real clear process or methodology, but they did find an opportunity. So the question is like, how do we automate this? How do we find things that when they happen tend to be associated with good things in the future that are likely to translate into experiments that are likely to be effective? So we go back to our three variable setup, right? Where we have X, T, and Y, which is exactly what we had here, where we have scheduled daily reminders. This is T, this is Y, and everything that happens before scheduling daily reminders, everything they did in the app is the X variable. And we can kind of slide this window along. Sorry, I inserted the slide accidentally. And just keep defining the treatment in different ways. Any event can be a treatment because of the way that we define this partitioning. So any event can be we can call it a cause. And what this allows us to do is just slide through the sequence and make anything be a cause. Anything can potentially, for a moment, we can relax our skepticism about the method and just say like, well, what if we just did this analysis of like what the effect of T on Y is for all T's. And we set Y to be something we care about. And then we studied every possible definition of T that we could come up with. Then our hypothesis space gets very, very large. And that allows us to discover potentially causes that we didn't know about. And that's the key idea, is that like if you do this analysis once, that's great. But if you really want to focus on discovery and finding things that are unknown to you, then you have to try more things than you know about. And so you have to cast a space of possible hypotheses. And so by streaming through the sequence like this, we're able to do that. And the key technology that allows us to turn this into an experiment is that we use a transformer model. And a transformer model, like we talked about for text, is capable of predicting the next token. So it's saying what will be the next word in the sequence, but in the context of events, it's actually telling us what the next event will be in the sequence. And by doing that, we have a score of how probable that they would use the reminders feature. Let's say it was a reminders feature as the treatment. We have a 14% probability of using the reminders feature as of that point in time. That's valuable information because what it allows us to do is to try to find users who have similar probabilities, but that didn't use the reminder feature, and they become our matched group. So you think about this as like we want to make a comparison between two groups. We want a treatment group. These are people who use the reminders feature, and we want the scores for all their probabilities. And then we want like some measure of some outcome here. This is the purple dot. So the green dots are the point in the sequence where they did the thing that was the treatment. The numbers come from the model that predicts like what the probability of them doing that at that point in time is. And in the control group, we're just streaming through the data and we're finding cases where the user had a positive probability of the treatment occurring, but then didn't. So they didn't take, in the causal inference terminology, like they didn't receive treatment, but they were eligible and probable to receive treatment. So they've become comparable because we know these numbers and we can try to match users. So here's a 56% user who didn't use reminders. Here's a 56% user who did use reminders. And I can this is like a comparable person, right? Because they had everything in that up until that point in time was summarized in this number, 56%. So this is a propensity score in causal inference methodology. And the result from propensity score modeling is that if you condition on the propensity score, like everything else in the history is irrelevant. So it's capturing all the relevant information about the confounding. So here's this e-commerce example that I've been kind of doing a bad job of explaining. But let's think about e-commerce setup where we have people can add things to cart, view detail pages on products, view pages and products, purchase products, remove products from cart, click on search results or run search queries. The green bars here are the estimates from that propensity score model for users who did get treatment or did do that event in the next event. And the gray bars are the ones that are coming from the model that are saying that they didn't do that event, and the probability is usually much lower because they didn't do the event. So the treatment group is green, the gray group is control. The problem is that they're imbalanced, right? So these are not comparable groups because these histograms aren't the same. If we compared the two groups of people who added to cart and never added to cart, that we would get like a lot of people who had no probability of ever adding to cart mixed in there, and they would be very low intent users. So we would be mixing together like a causal effect, which we want, with like confounding, which we don't want, which is that the people who don't add items to cart are just fundamentally kind of different users. But we can do what's called propensity score post-stratification. And by doing that, we just reweight the data. So we take the people in the control group, and based on their propensity scores, we upweight the people that look more like the treatment group, and we downweight the people who look less like the treatment group. And so just by changing the weights in the analysis, we end up with like this new distribution where the gray and the green are like perfectly symmetrical. It's not always true. So you can see like, some of the people who are removed from cart have a really high probability that is never matched in the treatment group. So we have to discard those people and say like they're not in the analysis, but there's some subtleties. But in general, we can treat this as like a machinery for finding a comparable group of people where their histories are balanced. Like I think of them as like they're similar enough that I'm willing to make a statistical comparison between these two groups. So what happens if we do this balanced analysis of comparing people who did certain events with people who didn't do certain events? Well, what ends up happening is that we have we call the raw correlation, which is like if we ignored X completely and just did the analysis of T, correlation between T and Y, that's this green dot. The green dots are typically larger and in the sense that they're further from zero, because they include this confounding, like the X variable is not accounted for. And so it's just a raw correlation. And so it's got like a mix of a causal effect and also some selection bias that we're trying to deal with. When we add our adjustment procedure that I was just describing using this LLM style approach, this pink dot was the adjusted effect. They move towards zero, which makes them more credible, in my opinion. Like most causal effects in most systems should be zero. Like if we studied every event in a system, a lot of them will be not meaningful. And we get sign changes, which is kind of important. So removing an item from cart has a positive correlation with purchasing, right? Which is like, it kind of makes sense if you think about it, is like active users are going to be adding items to cart and removing items from cart. So they're going to be more likely to purchase. And it's not because removing from the item from cart isn't helping them purchase an item. It's actually hurting them purchasing an item, but it's a signal about what kind of user they are. They're a heavy shopper who's really actually like kind of considering a lot of different products. But if we do this adjustment process where we adjust for how active they were up until the point where they removed an item from cart, then it becomes negative. So removing an item from cart has a small negative effect on your probability of purchasing. So this is telling us that that procedure that I was just describing is helping us make a better estimate than the raw correlation. It requires a little bit more machinery, but it helps us like get a more conservative and more correct analysis of the effect of T on Y. And we're going to do this for many, many variables. We want to get it as close to the correct answer as we can. So any event can be a cause, but also like concatenation of multiple events in a row can be a cause. An event in a certain setting, like a context, can be a cause, or what we call like dose level effects can be a cause. So like if you did something 3 times, and then what would happen if you did it a 4th time is an example of like a dose effect. So there's lots of ways in which we can enrich the hypothesis space and make it larger, and then we have to estimate more things. And that's good for us because we're trying to discover interesting causal relationships that we didn't know about before. So we can cast a really wide net for all the different kinds of analyses that we're going to do. And then we're going to hit go, and we're going to run a big for loop and run many estimates of the effect of doing a certain intervention on the outcome that we're interested in. And what does that look like in practice is that you end up with this kind of list of like many treatment effects, like all kind of ranked. And so each one of these dots and lines is an estimate from our model, from this methodology. And the dot is like our estimate of the increase in purchase probability from this specific cause that we have hypothesized in our study. And then we can browse through this and try to find, if we see things that are positive, we're going to look at it and say, can I imagine ways to encourage users to do more of this thing? if I see negative things, I can say, oh, can I imagine ways to prevent users from doing this, or like to make this less common in this particular situation? And by doing this, it's like it becomes like a kind of this tool for that quadrant that I was talking about, which is that like you can now, it's a browsing problem. It's not a statistical problem anymore. It's just, I already solved the statistical problem in an automated way. I can now go look through this and try to find if I see something that helps me spur some new intuition about what's going on. So just gonna wrap up so we can have a little bit more time for a discussion. The key thing about what I'm doing here is that is not all the fancy magic behind the machine learning model or whatever. It's just that like to do hypothesis generation, the only way to really do it is to generate many, many hypotheses. So you need to automate the estimation tasks and the hypothesis testing tasks. And then it kind of leads to an interesting question of like, how do we know that this method's working? And in statistics, like one of the biggest things that you can do is called like, most important thing you can do is validate your models and validate your conclusions. Like, are they valid? Did they pass the test? The problem with what we're doing here is that there's bias in the estimates because we didn't run a real experiment. And we also tested many, many hypotheses. So it could be that we just found one by random chance that happened to be look good. So there's two real important reasons why what I just showed you is likely to lead to incorrect conclusions, that we find a cause-effect relationship that doesn't really exist. The key here is that hypothesis generation it cannot be a scientific method on its own, that it only works when it's paired with confirmatory analysis, where we do that thing that the call map did, where we run the experiment and check and see. So a good version of the process that I just played out cannot be validated on its own. It can only be validated in concert with running experiments or running a more valid, rigorous causal analysis, and then figuring out if what you had predicted during your hypothesis generation task was then confirmed at a higher rate later. So I'm going to stop there, but that's kind of what I've been working on and the rough idea behind the methodology. And yeah, I'm happy to take questions and chat more about it.
Brilliant. Thank you so much, Sean. That was a fantastic presentation. Does anyone have any questions? If folks can raise their hand and I can call on you, or you can put something in the chat and I can read it out, or raise your hand and I'll call on you. Maybe while folks are thinking, from a um, focusing on the stats on the machinery aspect, the transformer approach that you got to towards the end, like that really jumps out as like a clear win. How do you then augment with data that are not sequential? For instance, I am a person that lives in Toronto. That's not a sequential data set. That data piece that remains in the constant there.
Yep.
How do you then
Yeah.
adjust for that? Yeah.
Yeah. So there's different ways to do it. Like the transformers are a very flexible conditioning tool. Like you can condition on anything you want. So one we have explored that idea by just inserting inserting events at the beginning of the sequence that represent that thing. So there's like at the very beginning of this, you can think of the concept of everything has to be an event. Then there's an event where like a user's born at T0 and they're born to be like a resident of Toronto. And that's like just an event we observe at the beginning. And the transformer can use that information and interact it with any other variable, any other event that's observed. So conceptually, it's really no different than an event. Now, there's some mechanical stuff about how you encode those things that we haven't done a ton of exploration on. But yeah, in general, like transformers are just so powerful that stuff like that is actually not too difficult to conceptualize how to get it into the model. But yeah, some mechanical stuff needs to be worked out.
If anyone has any questions, feel free to raise your hand. Otherwise, I might move a little bit away from the technology and move a little bit more towards the businesses. How do you think about solving short-term versus long-term aims, or equivalently, like finding local versus global maxima? Here I'm thinking, okay, like, let's just say we change the size of our checkout button. That might increase sales, but if it decreases the number of people that actually come to our website, ultimately, over the long run, that's a bad thing. How do you think about those sorts of things with your approach?
Yeah, it's a good point that we go back to one of the most important steps in this whole process is how you define the outcome of interest and which outcomes you're considering. And we talk about this in this causal discovery thing because in the causal discovery in the lower right hand quadrant, what we're basically saying is there's like a single variable we're willing to say like this is the business goal, and we're going to find all the things that contribute toward that. But in general, there's trade-offs, right? Like getting it's very difficult to get one thing to go up and everything else stays the same. And then the short term, long term trade-offs are a specific version of that problem where like in the short run things look good, but in the long run, maybe those users never come back because they weren't happy with their purchases, so they don't become repeat purchasers or something like that. So the key to that is to have like a vector value of outcomes, like as long-term and short-term things. They each could be different outcomes, and you could be measuring the effect on both, and then taking a look at the trade-offs that you face. The problem is that long-term outcomes are noisier and more difficult to estimate strong relationships with them. So if I wanted to say, will a user come back in the next 7 days? It's a lot easier of a question to answer than how many times will they use the product in the next 7 months or something like that. And in general, there's just a strong bias in these systems toward myopic behavior, right? Because it's easier to find things that work like on some short-term horizon than long-term horizon. So I would say it's kind of like an unsolved problem. There's some work on like statistical surrogacy that is pretty relevant here, but like probably way beyond the scope of this talk. But people are thinking about it, but also like it's a signal to noise ratio problem that might not be super surmountable.
Thank you. If does anyone have any other questions, feel free to raise your hand. And then finally, like very much on the business side of things. So when you were talking through, oh, Emily, so I'll just read out the question. Is there any concept from RLHF or general feedback loop where the model gets to learn for future problems from the human confirmatory analysis stage of what theories seemed more or less valid?
Oh, really nice. Yeah, I hadn't, no one's ever suggested that. It's a pretty nice idea to like, one of the things about the methodology I showed you is that it doesn't really leverage any of the advancements in LLMs at being very good at like reasoning. And I do think that it's a little bit of a bummer that we weren't able to figure out like how do you use like this plus like all the other stuff that's being developed to build like a real world model of like your business setting, because these aren't models that are like learning from every other company or just businesses in general. And I do think that there's something to like uh, figuring out how to marry these approaches where you can kind of have an agent that knows a lot about your domain and also incorporates all these empirical results so that it can kind of direct the search process in a better way. But yeah, certainly reinforcement learning would be one approach to doing that, but I haven't thought much about it. It's a really nice idea.
Are there any other questions from folks? Noting that we're now on the hour, so we should probably not take up too much of Sean's time.
I put my email address here, so if anybody's interested to chat more or like wants to hear more about this, I'm happy to do it over email. So feel free to message me. But otherwise, yeah, thanks for the opportunity, everybody. I really appreciate your time. Hope you got something out of it.
Fantastic, cool. Thank you very much for joining us, Sean. Really appreciate it.
Okay. All right. Bye, everybody.